Hello everyone, welcome to Chem Analysis. In this lecture, I will mainly discuss about some important formulas and some important concepts that you have to know regarding solid state chemistry. These formulas and information will help you to solve the questions related to this topic. So let's start this lecture. If a X-ray falls on a crystal plane and get reflected from this crystal plane, then the Bragg's equation for this constructive diffraction Bragg's equation will be n lambda is equal to 2d sin theta. Here n is a constant whose value is 1, 2, 3, etc. Lambda is the wavelength of the X-ray which is incident on this crystal plane. D is the interplanar spacing between the crystal planes. There are many planes for the crystal, and D is the interplanar separation between two planes. Theta is the incident angle at which the X-ray falls on the crystal plane, or the reflected angle at which the light reflects from this crystal plane. Is it okay? Now for the destructive diffraction, the Bragg's equation will be n lambda by 2 is equal to 2d sin theta. That means n lambda is equal to 4d sin theta. Here all the values are similar as given here, and the value of n is equal to, in this case, is 1, 3, 5. That is only odd values. For destructive diffraction, the equation, Bragg's equation, is n lambda is equal to 4d sin theta. Now, if you are given a crystal plane for which Miller indices is HKL, and you have to identify the interplanar distance between two parallel planes for this Miller indices, the equation, the formula for the interplanar distance is like this: 1 by d HKL square is equal to h square by a square k square, d square plus l square plus c square. Now if the crystal is a cube, then each side of the cube will be similar. Here ABC is the edge length of the crystal, and if it is a cube, then it is equal to A. Now if we put the value of A, B and C is equal to A, we will get we can write it as like this. That means the interplanar distance between two planes for which Miller indices is HKL, the equation for that is equal to like this, and provided the crystal is a cubic crystal for which each side length is similar. You have to keep in mind this formula also. Now if you are given two planes for which the Miller indices is like this, H1, K1, L1, and Miller indices for the second plane is like this, and if you have to calculate the angles between these two planes, if the angle is theta, then the formula is H1 H2 plus K1 K2 plus L1 L2 divided by h1 square plus k1 square plus l1 square into h2 square plus k2 square plus l2 square. This is the formula for calculation of interplanar angle between two planes. Now, if you have to calculate the density of a crystal lattice, density will be equal to mass by volume. If a crystal contains z number of atoms and mass of each atom is m, and the volume of the crystal, if it is a cubic crystal and side of the cube is a, then the volume will be a cube. Thus the formula for density for the crystal is like this: z into m divided by a cube. Now the value of z we can calculate depending upon the crystal nature. That is, if it is simple cubic or primitive, then z will be 1. If the crystal is BCC, then z is equal to 2, since z is the number of atoms present in the crystal lattice. And if it is FCC, then z will be 4. And m, that is the mass of each atom. Mass of each atom we can get if we know the atomic mass or atomic weight of the atom. If we divided it by Avogadro number, then we can get mass of each atom. That is the formula can be resolved to density is equal to z into, if the atomic weight is symbolized like m and the Avogadro number is written here, m by Avogadro number into a cube. A cube is the volume of the crystal. Then the formula of density will be like this. Now the next important thing for this is selection rule. Selection rule for diffraction from a given plane for a given crystal. Now for simple cubic crystal, the diffraction from a plane is possible for any value of hk and l. That is, it is allowed for a simple cubic crystal for any value of hk and l. For BCC crystal, the allowed transition for HKL plane will be possible when the summation of H, K and L will be even. Then it will be allowed. If the summation is odd, then the diffraction is not allowed. In case of FCC crystal, the allowed value for HKL is all odd or all even. Then the transition or diffraction will be allowed. But if there is mixed value, that is odd plus even, then the diffraction will not be allowed. Is it okay? Now if you are given a plane like 1, 1, 2 plane, just suppose take a plane for which Miller indices is 1, 1, 2. Now to see that which type of crystal contains this plane, we have to first see the condition for FCC and BCC, then go to simple cubic crystal. If this two crystal is not possible, then we have to think about simple cubic crystal. Since that diffraction is allowed for simple cubic crystal for any value of HK and L, so if a plane is given, then that plane must belong to simple cubic crystal. So we have to first see that it belongs to FCC or BCC, then we have to go to simple cubic crystal. If the plane satisfy the condition for any of these two crystal, then we have to say that the plane must belong to that crystal. So for this crystal, if we see the condition of FCC or BCC, for FCC we have to satisfy the condition that all odd value or all even value. But this condition is not satisfied here, since one is odd and 2 is even. So FCC is not possible. For BCC crystal, we have to sum up this value and we have to see it is even or odd. Since it is 4 and it is even, so we can say that this plane belongs to BCC crystal and the crystal's type is body centered cubic. If the given plane does not belong to any of this crystal type, then we can say that that plane belongs to simple cubic crystal. Is it okay? So these are the things you have to keep in mind to solve the questions related to this topic. So that's all for this discussion. In my next lecture, I will solve some previous year questions on this topic. If you like this video, then please share it and please subscribe to my channel. Thank you.